Hi, good morning. We will be starting in around 10 minutes. Thank you for coming. That's a really cool picture, Jacob. Where did you take that yourself? That picture? It's really cool.
No, I find beautiful pictures on the internet and then I share them with the world.
Nice. I like it. What do you know what type of bird this is?
No, but it looks like a hummingbird, but it's like a really paradise looking
Yep.
hummingbird.
Yeah, I thought so. Maybe a hummingbird. They are so cool. They are amazing. Hi, Catherine. Oh, go ahead. I wanted to say something.
I heard immediately my mind went to the statistic hummingbirds have hearts the size of a pencil eraser.
Yeah, and they beat so fast. It's so fascinating. It's amazing. Hi, Catherine. Hi, Yassine. Welcome from France. Cal. Hi, Victoria. How are you today? Hi, Cal. Come up. We are waiting for a guest speaker. Hi, Cal. How are you today? Still are waiting.
Hi, hi Katerina. Hi everyone. So what's the topic, Katerina?
Do you see the link on top of the room? So it's about
Yeah,
quantum physics. Usually, electrons should have one type of frequency, but recently, this group has discovered that they can have more than one at the same time, which is really intriguing. And yeah, we will learn all about it today here. And yeah.
what basically discover is electron have more than one frequency. That's the discovery.
Yeah, if you want to go to the link, or just listen until our guest speaker, because he will present. He will present the data way better. So they can have different spins and charges.
Yeah. So for the time being, can I explain something about quantum mechanics, which I know?
Yeah, go ahead. But when the guest speaker arrived, I will just to let you know, will interrupt you. It's not nice, but we have him only for a certain amount of time. So,
Yeah,
it took time to plan this. That's why I will then interrupt you. Okay.
right. You are right. I will stop after some more speaker will come. So basically, if someone is new to quantum mechanics or in the audience. So basically what quantum mechanics is, it is actually the phenomena occurring at the transitional zone between the mass and energy. And here we see certain, certain phenomena which is very difficult to comprehend because it's a transition zone. Wave matter is constant fluctuation. So that's why here we need a different kind of physics, different kind of mechanics. So this is a basic definition which I can give about the quantum mechanics. I think more speaker have come, so I have to stop.
Hi, Pedro. How are you today? Thank you for coming. To unmute, it's all the way on the bottom.
Hello.
Yeah,
Hello. Can you hear
perfect.
me?
Yes,
Hi.
we can hear
Perfect.
you. Thank you for coming.
No, thank you for inviting me. It's great to be here.
Another person from Porto. I'm also originally from Porto, but
Oh, hola.
but I didn't grow up most of the time there. So
Well, I mean, strictly speaking, I spent most of my time in Porto. I'm actually from a town just outside Porto called Povo de Varzim.
okay,
But yeah, I mean, I spent my life there until,
a
well,
friend of mine. She's also from Porto, I think Rosa, but I don't know from Gaba. I don't know if you know Gaba. And
yeah.
yeah, yeah, I was a Gaba student, and then I went abroad. So that was the longest, I spent as a grown up, being in Porto, living in Porto.
Yeah, same. I mean, I left Portugal almost 8 years ago. But yeah, I mean, most of my life was there.
Wonderful. It's a great place to be. The best
Yeah,
place.
no, I agree. Exactly, exactly. Better than Lisbon. Better than Lisbon.
Oh, yeah, definitely better than this. I don't know if nobody, realizes, but there's like I think it's very common in European cities, right? In general, to have like in the same country like a city that are kind of, you know,
Rivals.
yeah, kind of rivals. So
Yeah.
yeah. So yeah, we'll wait a few minutes. Golda, I invited you to speak. I don't know if it's working. I see you raised your hand. If it doesn't work, then please just restart the room. Like, come back in again if it doesn't work too. Or try to click on your profile, and then on the bottom you should see the invitation. So, okay. Hi, Frank. How are you today? Meet Pedro. Um, Frank here is one of our
Hello.
moderators.
Good evening. I'm fine.
Hello. Hi, Pedro.
Yeah, let me. Yeah, everyone is saying welcome to Clubhouse. I hope you did. You get to use your account in the meantime a little bit, or I don't know if you went to some rooms or something.
Mm, Me, yeah, I had a chance to explore. It's fine.
Okay, good. Yeah.
Yeah, that's it's very intuitive to use, and yeah, I think I know more or less how it works now.
Yeah, there's some interesting rooms here. Like clubs and rooms. There is the our club, of course. I also like to listen sometimes to tech news around the world. Sometimes it's good to get updates there too. And yeah, I don't know if you have recommendations of some rooms and clubs.
I will have a recommendation. That is It's About Time Club with Paul Burrow. There are a lot of, what is it, physics? I always mix the physicians and what are the others? But a lot of
Physicists.
physics people in there, and it's really fascinating. And they all have loads of replays with extraordinary people.
Yeah, I agree. That one, I almost forgot about that one. That one is great. And I think we can start. So welcome everyone to Science Society, and of course a special welcome to Pedro. He is joining us here today to present his work, his fascinating work. And before we start, let me give you a little bit of an introduction so you get to know him a little bit. Yeah, as I mentioned before, who was here before, Pedro Vianez, Vianez is originally from Porto, Portugal, just like me. And he is since 2022 a doctoral prize fellow at the Integrated Quantum Materials Group in the Cavendish Laboratory at the University of Cambridge. And he did his master's. He did his bachelor in physics at the University of Porto, and then he did his master's in physics at UCL, and his master's in optics and at the Photonics and Imperial College. And in 2019, he was also a visiting assistant in research at Yale Quantum Institute. And after that, he went to Cambridge to did his PhD. And he was a member of the semiconductor physics group, and also in Cambridge. So Pedro's work mostly focuses on how electrons interact with another when confined to lower dimensions, or where quantum effects are strongly enhanced. And he reported the existence of previously unknown state of matter, and he has expertise that includes device fabrication, electron beam lithography, low temperature, low noise, and high pressure measurements. And currently, his main research interests include strongly interacting many body systems, quantum spin liquids, thermoelectric, and energy harvesting. Yeah, so we are very honored to have you here. Your work is really fascinating. And before we start, if that's okay with you, we usually ask like a couple of questions are like more broad. So how did you find interest in science? Was it always something you were fascinated about? Like, was it a teacher or some great class you took or something interesting you saw, you read, and we think it's kind of interesting story to hear.
Okay. Hi, everyone. Thank you, Katerina, for the nice introduction. How did I start in science? So just to check, can everyone hear me? I never know if
Yep.
my audio is working.
Yeah,
Yeah,
absolutely
okay,
fine.
great. Yeah, how did I start in science? I mean, I guess, I mean, normally in Portugal, when you're doing the standard high school curriculum, it's when you start 10th grade, you have to choose between science, economics, humanities, and arts. And it was between these four, it was always pretty more or less clear to me that I would go down the science track. Now, I didn't know at the time whether or not I would want to become a scientist or even study that at university. Um, then, sort of eventually, let's say a year in, I thought I wanted to become a chemist, and I really liked chemistry. Um, but the more I studied chemistry, the more I realized that, and I hope there's no chemists hearing, listening to this, but no, I'm joking. But yeah, the more I realized that actually once you start going down to the very um, details, it really physics and specifically quantum mechanics and quantum physics. And I guess that's more or less when I decided I'd like to study physics at university, or at least to explore it. I wasn't sure whether or not I would like to do research. That came a bit later. But yeah, during my when I was also in secondary school in Portugal, we have and like in many other countries, there's this thing called the Science Olympiads. So I did that in physics, and that also allowed me to start learning a little bit more beyond the standard curriculum before university. And yeah, it was more or less that. So then I did my undergrad, and after my undergrad, I had the opportunity to move to the UK, and that's where I've been since. First to do my master's, then my PhD, and that finished 2-3 months ago. But I think it's just a very standard story. I always liked math and science and solving problems, and I like being in the lab.
Yeah, that's great that you kind of went for what you were always kind of passionate about. That's
Yep.
interesting. And for this project here, was there like is there like a story behind how did you come to join this group? And was it, I don't know, easy to get grants for it? Or is there some background story for it?
Yeah, there is actually. So I started my PhD in 2017. And so I was applying for this in 2016. Now you might know that in 2016 something happened in the UK, Brexit. So of course, initially I was applying for a PhD program which I had been accepted to at NPL. It's called the National Physical Laboratory, and that's where I was going to go. But then, of course, as a at the time EU citizen, with Brexit happening, funding became very uncertain. And so suddenly I had this sort of offer for PhD, but the funding wasn't guaranteed. At the time, it happened that the university, so the NPL is a sort of like a research lab. It's not a university, so they need to be affiliated with the university to grant degrees. And it happened that the NPL and this specific project was affiliated with Cambridge, and specifically the semiconductor physics group there. So that's how I met my supervisor. Then, of course, because of funding, I ended up moving to a slightly different project, and that had funding coming from somewhere else. But that's sort of how I made my way to Cambridge and to specifically the group where I did my PhD. And so, yeah, that's sort of the story. This specific project, it's quite an old project. So there's two PhD students before me who I can trace back some of the early work. I'd say at the beginning of my PhD, it was sort of something which we thought would be relatively quick and easy to do and straightforward. But then it, like is often the case in science, you start seeing one more thing and another thing and another thing, and then suddenly it's been 3-4 years. And what I initially thought this project would lead us to, it led to completely different directions we weren't expecting. But so that's sort of how I ended up doing this for the past 4 years.
Wow, that's interesting. Yeah, that's so yeah, that's interesting that you let yourself lead by the data and you know.
Yep, pretty much.
Exactly. Okay, so yeah, now the floor is yours basically. If you feel free to let us know if you're fine with us interrupting while you talk about your work and your project, or if we should wait with questions till later. So yeah, the floor is yours.
No, I'm happy. Anyone, feel free to ask any questions at any point. I was just wondering, so would you like me to just very like give a sort of a very general view of the paper and sort of what we did and why we did
Yeah,
it?
yeah,
Would that be? Yep. Yeah, so this paper, I think the link is somewhere here, but it's on Science Advances. It's open access, so hopefully everyone should be able to open it and download, and there won't be a paywall. It's also on archive. And basically, before I get into the details of the paper, let me just try and explain a little bit of what we're doing and what's in what context was this work being done. So basically, if I had to summarize my research in one sentence, I basically would say that I study electrons, so fundamental particles in nature, inside solids, and probably anything that any material, any object surrounding you right now. It's made up of atoms, and as you know, there's a nucleus and there's electrons around it. So I'm not so interested in the nucleus. That's nuclear physics. I don't do that. I'm interested in what's around the nucleus, so electrons. And we live in a three-dimensional world, so that's most things that surround us. But turns out that recent technological improvements for the past few decades actually allow us to confine electrons to different dimensions. So probably everyone has heard about graphene. So that's a two-dimensional material. Essentially, electrons there can only move in a 2D plane, x, y. You have also other things, semiconductor quantum wells, thin film. So these are all structures and materials you can make in a lab and industrially in some cases where electrons can only sort of live in this two-dimensional world, sort of like flatland. We can actually take this to the next level, and you have one-dimensional system. So that's, as you can see from the title of the paper, is the sort of system we use, things like semiconductor quantum wires, but also carbon nanotubes, so their electrons can only move along one direction. And actually, you can take even this a step further and go to zero dimensions, essentially where you have strong constraints along x, y, z. And so those we normally call quantum dots. But so what's interesting about playing with the dimensions is that the way electrons behave can change quite drastically. And that's essentially why people are interested in different dimensional systems. They're looking for interactions, and specifically, they're looking for strong correlations. And so now you can ask me, why do we care about strong correlations? And these correlated states, which again is also another word you can see in the title, strongly correlated one-dimensional conductor. The way, so this goes by many names in the field. You can call it, in the literature in physics, you'll hear this as many-body phenomena. More recently, there's a sort of a better sounding term, we call it emergent phenomena. The idea behind this is, I like to think this in terms of birds. So if you think of a bird, one bird, and you study everything there is to know about that bird, then my question to you is, would you be able to predict the patterns that emerge when groups of birds come together, flocks of birds? And the answer is probably no, because that's a group behavior, it's not an individual behavior. And so it turns out that electrons behave in the exact same way. You have one electron and it can do its things. Particle physicists study that. But then you bring a bunch of electrons together and you start having this collective emerging phenomena, things like superconductivity, forms of magnetism. And they're really cool things to study because your material and your system can start behaving in a completely different way. And so 1D is interesting because in 1D, you always end up with these states where these correlations arise. And you always end up with this interesting new phases of matter just because of geometry alone, geometrical confinement. So that's why we go to 1D. We're looking for these new types of emerging properties, let's put it like that. It's sort of like if we go back to the bird analogy, it's sort of like you start with individual birds, but then you put them together, and suddenly instead of birds, you start seeing geese or elephants. I don't know. You start seeing other things. And of course, quantum mechanics also comes in play, and that's where things start getting very non-intuitive. But so talking specifically about this system, so essentially here we were looking at a one-dimensional system of electrons. And this is strongly correlated. So if you picture yourself in a corridor, a very narrow corridor, so you can't go to the sides, there's people in front and behind of you, there's no way for you to do anything without bumping into those people, or you can't get out with them without those people also moving. It's the exact same thing with electrons. If they're confined down to these wires, the whole thing behaves as a whole. Essentially, you stop having individual electrons, you start having group collective behavior. And so what's interesting about this is that so electrons as particles have properties, spin and charge being two of those. So you might remember or know from early science courses. So the electrons are negatively charged particles. Spin is a quantum property. It's not very important to go into detail what it is, but you can sort of think of it as if you think of an electron as a ball spinning, it can sort of spin clockwise or anti-clockwise. That's sort of like it. But so these are two properties that electrons have, and they normally together. So electrons as a fundamental particles, as far as we know, there's no such structure. So these two things are together. When one thing goes, the other also goes. But so what happens in 1D, and what was quite exciting, was that actually in 1D, these two things separate. They split. It's sort of like a spin goes in one direction, charge goes in the other. If you read the press release behind this paper, we sort of came up with this analogy of a slow and fast lane. Essentially, the idea is if you're driving your car and there's a slow and a fast lane, now imagine that suddenly half of your car goes down one lane and the other half goes through the other lane. And because they have different masses, they'll have different speeds, so one goes faster than the other. That's sort of what's happening to the electrons in these 1D systems. The spin and charge split as collective excitations, and one has a higher mass than the other, and therefore one propagates faster than the other. Now, this result had sort of been known, just to give you a little idea. Theoretically, this can be traced back to the 50s by two people, Tomonaga and Luttinger. So the theoretical model, for those more interested in that, behind this, it's called the Tomonaga-Luttinger liquid model. The theory sort of was introduced in the 50s and then finalized in the 80s by Haldane. Experimentally, there was sort of some evidence about this in the 90s. I would say that strong evidence for this separation of spin and charge came around the mid-2000s, so about 10, 15 years ago. So that had already been known. So that's sort of where the field and the literature was when I started my field. Now, what I haven't mentioned yet is that all of this that I've said has a caveat, and that is that this is only predicted and expected to work at low energies. And so the fact that spin and charge separate at low energies wasn't new. Like I said, experimentally, it's sort of been observed by two specific groups. So one was my group, the other, there's also another group who did similar measurements. And that I think was sort of clear evidence for this property. Before that, there sort of were many different setups, sort of kind of seeing it, but not very clearly. But all of this was known to happen at low energies. And so what was interesting about this paper and what we saw was not so much a separation between spin and charge. Like I said, this was already known, but more the fact that this now was happening not only at low energies, but also at very high energies. So the assumption in the field was that anything like this collective properties at high energies would completely disappear. They would sort of be washed away. And you can sort of think of this because if you think of most of things you've heard about quantum mechanics, they normally work either at low energy, low temperatures, or high pressure, or low vacuum, or very small systems, so nanotechnology, you normally don't see quantum effects in the macroscopic world at room temperatures and so on. And there's a reason for that, is because things tend to get smeared out at high energies. The fact that we were starting to see these excitations at very high energies, and if you want me to put a number to it, approximately 5 times higher than what we were seeing before, was very surprising, because then the question was, how? How is this not breaking apart? And so that's sort of what, in non-technical terms, what the separate spin and charge Fermi seas mean, is that we went from having a feature at low energy to actually having something along the entire band, and that's what we call a Fermi sea. So yeah, so that's, I guess, a sort of a very brief introduction of sort of the field and what the motivation was and what the main result was. I'm an experimentalist, by the way, so on this paper, most of people, apart from Alex Sipliatev and Andrew Schofield, most people are experimentalists as well. So, yeah, so if you're looking at the paper now, in Figure 1, Panel B, that's where you see what the device looks like. This is a semiconductor device that you can make inside the clean room. You can see the scale there, but for example, our wires are about 50 nanometers or so. So if you think that, to give you an idea of the size, I think the width of human hair is between 1 and 100 microns. So a nanometer is 1,000 times smaller than that. So this is maybe 100 times, 1,000 times smaller than the thickness of your hair. So that's the system. We can actually change the densities. The lowest densities we actually went to was about 17, 18 electrons per micron. I find this quite cool because normally, again, if you're a chemist, when we think about electrons, we think in terms of maybe Avogadro's number, 10 to the 26. We can't really imagine big numbers. If I tell you to imagine 10 objects or 100 objects, you can. If I tell you to imagine the difference between 1 and 10 million, probably looks the same in your head. But 15 is actually something you can picture in your head and imagine. And the system is 15 electrons. Then, of course, we have these arrays, so you multiply that by 400. But to me, it's quite exciting that just essentially measuring a signal coming from 15 electrons interacting with one another, or 18. I think that's quite cool. Yeah, so that's what the device looks like. There's a number of gates. I won't get into the technical details, but essentially by playing with those different colored gates, that allows us to set the tunneling conditions so that we can actually probe this system. The technique we use, tunneling spectroscopy, it's sort of like a microscope. It really, basically, you have your probe and you have your system of interest, and we're mapping that system. So we can observe its excitations and details. And so the sort of maps we do is what you see, for example, in Figure 2C. And then you look at these maps and you start looking at resonance. So the white bits between the red and the blue, so that's a differential. So the white will be a peak or valley, a maxima or minima. And you start seeing these resonance, but you see them with different slopes. And I can actually tell you a little bit more about Figure 2C. And the story behind this. So if you are a condensed matter physicist and if you studied free particle systems or particles that behave like free particles, you'll know that they sort of follow a parabolic dispersion. It's a parabola. And so when we first measured this, that's what we were expecting. We wanted to see a parabola, and we were trying to fit our data with a parabola. And I couldn't. I kept trying it, and no matter what I did, a parabola just wouldn't fit. And of course, I would tell this to my supervisor, and he would come back to me, tell me, well, one of your parameters is wrong, so you need to calibrate for this or that. So all these curves you see, there's a number of parameters behind it. And so we kept thinking, okay, maybe the thickness is wrong, or the mass is wrong, or the capacitance are wrong. And then we went and we simulated, or we went and we measured using a different technique. And we kept getting better and better constraints in these parameters, and still we couldn't fit this with a single parabola. And so this was more or less at the end of my second year, and that's when I had the opportunity to go to Yale for visiting the theory group. So like I said, I'm an experimentalist. I had a lot of data to analyze at that point, and it was quite good to just get away from the lab because being surrounded by theorists, there was no temptation to go and do more experiments. And so it was at that point that we sort of, so we had this preconceived idea that we should see one parabola. And then we tried and tried and tried, and we couldn't see it. And it's at that point that we started thinking, okay, if we now think our calibration is right and we can't think of anything else that could explain this, maybe that's it. Maybe it's not one parabola. And then the question became, what is it? And so that's where theorists might come in handy, because then they can give you ideas, or at least things you might try and might work. And so that's when so the panel in figure 2a, that's the theory prediction. So that's when I came across that picture, and that was proposed to me. And then the second I fed it to my data, within probably less than a month, we were getting very good fits like we didn't see before, because it turns out that it wasn't one parabola, but it was two, which in hindsight is obvious, because if you think of spin and charge separating, you would maybe say, okay, maybe you have one parabola associated with each, one with spin, one with charge. But for the first 2 years of my PhD, it wasn't obvious. And we kept trying to do this with just one single parabola. So that's why you see the green parabola in figure 2c for spin, and the magenta one for charge. What was surprising was really that up to before, and if you see the papers before this, you only see one parabola there. And that actually, we now believe, I wouldn't say was wrong, it's more that our calibration at the time didn't allow us to resolve that. So we thought it was one, and we were happy with it. And so that's the main result, and that's from there that this two Fermi C story and separation of spin and charge can be inferred. Then there's two other small results, just to quickly wrap up, that this paper also has. The first one is in figure 3. We call them the replicas. Really what they are sort of like echoes of the main mode. You can sort of, if you shout in a room, you have the main, so there'll be a loud noise, and then you might hear some echoes, which are weaker and damped. So these replicas are sort of like echoes of the main mode. What's exciting about this is that, again, this is not predicted by the original theory, so it was completely new. And these echoes are expected to depend on length. So that's why, for example, in panel B and in panel C, you see little lengths from 1 micron all the way to 18 micron. And you see that as we change the length, the strength of these features also changes. So this was completely new. The theory didn't. There was sort of a theory that predicted this, but that theory was originally spinless. And of course, if we know we have spins, there's no such thing as electrons without spin. So the theory sort of like gave us an idea of maybe what we should see, but we knew from the start that the theory couldn't be complete because it didn't include spin. But so that was when I first started my PhD. This was exactly what I was hoping to observe, replicas. I thought this was, if you had asked me 4 years ago, sort of like what I wanted the main result of my PhD to be, it would have been this replica story. And we did see it, but it turned out to be more of a secondary result compared to the main result, which was the two Fermi C story. Which, again, I think it's often the case in science that you start doing something, you think you want to prove this hypothesis or see this, and then in doing so, you end up stumbling across something else. But yeah, so that was the replica story. Again, you can think of this as echoes. Again, one of the non-intuitive things, I guess, that happen in 1D. Because, by the way, I maybe I should say it clearly, but none of this, at least separation between spin and charge, replicas, as far as we know right now, none of this happens in 2D or 3D. It could. There's people working in that, but I would say, while the theory in 1D started in the 50s and the experiment only came in the 2000s, 2010, and now, I would say that in high dimensional systems, the theories probably started 10 years ago, and the experiment may come in 30, 40 years time. I don't know. But yeah, none of this so far has been observed in high dimensions. And yeah, just to conclude then, the final result, I mentioned there's three results. One is the spin charge, the other is the replicas. The final one is in figure 4, which was we were just started to play with how many 1D systems we had. By sort of, I don't want to get into technical terms, but by changing the density, you can go from having one channel to 2 to 3. So we call those subbands. And then once you have more, they start to screen each other, electrically screen. It's sort of like when you have blinds and you close your blinds so that the sun doesn't come in. It's sort of like that. It damps the main signal. And so that's we started playing with that because, of course, fundamentally what we're doing here is we're playing with the Coulomb interaction. And by screening, you can make it weaker, you can make it stronger, you can make all these effects depend on the strength of the interactions. So that allowed us to do a systematic study on that, and that's just what's shown in figure 4. So yeah, that's a very quick overview of the paper and its main results. Now, maybe just to conclude, you might ask, okay, this is all very nice and fundamental physics and whatever, but why do we care about this and what's interesting mostly? And at least the way I see it, the most exciting thing about this work was that, like I said, you're saying everyone working in quantum materials and solid state physics, we observe these amazing phenomena, but we observe them at very low temperatures, so close to absolute zero, something like minus 273 degrees Celsius, or I don't know how much that is in Fahrenheit, but that. We observe them at very high pressures, thousands and thousands of atmospheres. We observe them under conditions which we don't live in. Ideally, we would like to have something that was superconducting at room temperature or at ambient pressure, or at least that didn't require such extreme conditions. And that's really sort of, I would say, the holy grail of condensed matter. And so the problem is what I was saying, all these excitations, they sort of disappear, they smear out, they get destroyed once you go into the high energy regime. And what we're starting to see here is at least, and of course, I'm not saying we're nowhere anywhere close to having it at room temperature, but essentially the most exciting thing about this paper was that we were seeing these excitations at quite high energies, and that was surprising and that was quite exciting. And of course, then that raises the question, can we do this in high dimensions? Because of course one-dimensional systems are hard to integrate, but in 2D you have graphene, in 3D you have everything that surrounds you. And can we somehow replicate this there, where you have, so that you can bring these properties out of the quantum world, or they'll still happen because of quantum effects, but make them more useful because they're happening closer to the conditions we live in. So this is more or less what I'm working on at the moment. I moved sort of from semiconductors to the more general field of quantum materials. Of course, there's more direct implications of this study. So this result right now is another project I'm involved on that was mentioned at the beginning, is what we call energy harvesting. So maybe we don't need to go to room temperature, even if we can raise to 1 or 2 Kelvin, that's the temperature of outer space. So then you can have these things working at very cold temperatures, but if they're working inside a satellite, that's fine, because it's a temperature of outer space, and would be a big field of research is how to produce or harvest energy in space to power satellites, rockets, I don't know. So that's one of the things I'm looking at the moment. The other thing, just to conclude, is part of this thing called the European microkelvin platform. So everything you see in this paper, the lowest temperature at which it was measured was 300 millikelvin. And actually right now, so I've been here for 3 weeks now, we wrote a grant to go into the ultra low temperature regime. So currently this same sample you see in the paper is at 5 millikelvin. So that's 2 orders of magnitude colder. And you do see new things. once you get colder sometimes. That was what I was hoping for, and we think we are seeing those. But yeah, at the end of the day, it's exciting to play in these conditions. It's very far away from where we live, but yeah, you would then like to hopefully make it use of this and improve the technology. And yeah, that's I guess what people do in condensed matter, and that's sort of, I think, a quick overview of the paper. And if anyone has any questions or something that wasn't clear, I'm happy to discuss it.
Yeah, thank you so much, Peter, for this really great presentation of your really cool work. I want to give people a chance to ask a question. So I saw Ben, you joined the stage too. Jacob, Frank, if you have a question, press your microphone. Go ahead, Ben.
Hey, Pedro, thanks for the interesting presentation. I seem to have stalked you around the world. I too went to Imperial and now live in Cambridge, so great to hear from you. In figure 1b, where you talk about SB, are they something like sidebands in radio? Is there anything? I think you're calling them subbands, but is it a completely different thing, or does it have a similar mechanism to sidebands?
Sorry, can you say that again? Figure 1b or 1c?
Yeah. Well, so in figure 1 in general, you've got things marked as SB. You're calling them subbands.
Yeah,
Wondering if
subbands. Yeah.
are they anything like sidebands you would see in radio, the harmonic
No.
sidebands?
So that was just a sort of the term that got popularized in the literature. So normally when you, it's not, so you'll see that right at the top of panel C, I wrote there 2D band. And actually, if you go the full map, that is not on the paper, but it's in my thesis. Normally when in condensed matter, this kind of dispersion relationships we call bands. And in the case of 2D, that's why you have a 2D band. The way we create our 1D system, what we do is we start it as 2D. You can think of sort of like a plane of electrons, and then you start to squeeze the electrons from the side so that eventually your plane becomes a line, of course with a finite thickness. So strictly speaking, is not perfectly 1D, but it's what we call quasi 1D. And so when that happens, the main band splits into multiple bands, which are below the band, and therefore we call them sub-bands. And that's why you see 4, 3, 2, 1. So the sub-bands, which are below the 2D band, is when we see this transition between 2D and 1D behavior. So this was the first measurement we did, because of course, if you start doing an experiment and you say you're working with a one-dimensional system, then the first question people will ask is, how do you know it's 1D and not just a very narrow 2D? And you can show that by showing that the band splits and becomes multiple bands, which we call subbands.
Wicked, thank you.
Yeah, thank you for answering that. In the paper you describe, you had to kind of basically refine or change the methods you were measuring, which is similar to a spectrometer, I read, and this photoemission spectroscopy. So how did you had to basically adapt the measuring system to be able to see this result?
Yeah, so the technique is called magneto-tunneling spectroscopy. I guess, I can sort of trace back the original proposal and the original idea almost to, I think, 98, 99. Again, mostly on the theory side. And then there were people doing this with in energy, but not in momentum. So in our plots, in our maps, like figure 2C, essentially the x-axis is momentum, the y-axis is energy. So for those familiar with it, this is what we call a dispersion relation, but that's not the word's not very important. But essentially, yeah, the technique was originally proposed in the end of the 90s. Then people started doing this in energy, but without momentum resolution. Momentum is tricky because of you need to your design and the way you engineer this device needs to be very well calibrated. Otherwise, you'd need huge fields, and you wouldn't be able to do this in a cryostat. You'd have to go to a cyclotron facility or something like that, which, of course, then for other reasons we wouldn't be able to do this measurement. Yeah, so normally when I try to explain this technique, this really is a microscope. In the same way you look at cells under an optical microscope. Now, of course, it looks more like a quantum tunneling microscope, for example, rather than a classical optical microscope. But again, that's just because what we're observing is very small, and of course, optics wouldn't work. But if I can get just a little bit more technical, really what this is spectroscopy. So a very well-known technique that you mentioned is called ARPES, which is angle resolved photoemission spectroscopy. There, what you're basically doing is you're shining light, you're sending photons to your sample, and then you detect the electrons that get kicked out. And basically doing this measurement for different angles and different intensities allow you to sort of map the band structure again of this crystal. So it's a very well-known technique. It's used amply. But this technique is a surface probe. So basically, it only allows you to measure the top few layers of atoms at your sample. What we're doing is basically something similar to that, at least in principle, it's the same thing, but we're not at the surface. The system actually, so that in figure 1B, what you see there is an SEM, a scanning electron microscope picture of the device, but the actual system, what you're seeing is the surface. The actual system is buried below the surface, 100 nanometers or so below the surface. And maybe that may sound like it's not a lot, but actually when it comes to layers of atoms, 100 nanometers is huge. So ARPES wouldn't help us here because, like I said, ARPES, photoemission spectroscopy, only probes the very top layers. And so what we're actually doing is we have our system buried below the surface. Now you can ask, what advantage do you get by having a system that's buried rather than a system that's at the surface? And the quick answer to that is that the system is much more robust, it's much more resilient. Because in ARPES, you need to be under high vacuum. Any kind of impurity, any kind of defect, any kind of fracture will impact your signal. While if now everything is just buried down, it's protected from atmosphere, so I don't need vacuum to do this measurement. I literally can grab the sample, it's sort of like 1 centimeter by 1 centimeter, the actual chip carrier, not the sample, and I can move it around. I normally don't because then other things could happen. But if I wanted to, I could almost throw it against a wall and maybe it would survive. I don't know. I'm not going to try. But it's much more robust than a typical ARPES measurement. So yeah, that's a technique. Basically, what we had to do then was, so of course you're seeing the devices that work, but this was actually a lot of, so in total there's 6 different devices in this paper because we were doing a study in length and we also wanted to collect statistics to make sure that we weren't just observing a fluke. But before that we had different generations where we were playing with the dimensions, where we were sort of like getting the technique right. So one thing that's, I'd say maybe unique about this sample is that you might see that there's normally when you do fabrication chips and sort of things that are inside your phone and your computer, everything, all of that is flat. And if you look at the picture, you will see that there's these little bridges that are actually suspended. So they were fabricated in 3D, not 2D. And there's actually another paper, it's on somewhere in the citations, it's an applied physics letters paper, but that's literally just about how to fabricate those structures. So there was a lot of iteration and fabrication improvement that we had to overcome in order to get this device to work. But yeah, once that was that, then we were able to use the technique and then collect the data, and then the question was how to analyze it. Yeah, I mean, the technique itself is just like a very powerful, high resolution microscope, I guess. Because again, at the end of the day, remember, at its very limit, we were probing and studying the excitations of between 15 and 60 electrons. So if you want to see something, you need to have very good resolution because the signal gets very very small.
That's really fascinating. And just, for in general, for people to know, do you collaborate then with engineers to, improve the technique? Like, is it a big collaboration work?
Yeah, no. I mean, if you just look at the authors list, so of course, so there's me. The second person was a PhD student. So the second, third, fourth, fifth, and sixth person were all experimentalists at different stages. So Anne, for example, had the idea for the background, so that was part of the calibration, and Keith had the idea for smearing the fringes, which is also a parasitic effect that sort of clouds what we see. Yuchin and Wecat were probably the two people I worked most closely with, but so these are sort of the core group of people in my group. But then you have John Griffiths, who did the E-beam. Ian grew the material. So I often say there's two things I didn't do in my PhD. So I can say that I fabricated a device, I did the measurements, I did the analysis, I wrote the paper, blah, 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 blah. But there's two things I didn't do. First one was grow the crystal. So that was done by Ian, the wafer. So the actual material where we fabricate this. And there's actually lots of physics that go into that, and it's not something you can just it's not trivial. Let's put it like that. And do the E-beam, so the electron beam lithography, how you create these very small structures. That was done by John. David is one of the lead PIs. Andrew is again another lead PI, but on the theory side, and Alex. Also the theorist we collaborated, and Chris was my PhD supervisor. But of course then, for example, the time I was at Yale, that was all the group of theorists. We collaborate, not maybe for this specific project, but in other projects related to this, we collaborate with material scientists. Probably that's closer to what I'm doing now in quantum materials. But yeah, you do have, even within physics, you do have lots of people with different expertise, whether that's crystal growth, clean room fabrication, very sensitive measurements. For example, now I'm in Switzerland, and the reason why I'm here is because they have facilities and equipment that not many places in the world can reach very, very low temperatures, like 5 millikelvin. So I didn't have that at Cambridge, but I have it here. So yeah, like everything in science these days, it's you also have strong collaborations both on the experimental and theory side. And I think if you just go to any journal and start opening papers, mostly experimental papers, you'll see that there's often quite a lot of authors, partially I think because of that. But yeah, it's very strong collaborations.
Yeah, that's interesting. And will any of will maybe this technology development that you also did, will those be applicable to some, I don't know, quantum computing, communication? Will there be maybe one day some application, you think, for like the wider?
Yeah, so I guess that's the hope. The hope is that if you now, I'd say right now the ball is more on the theory side, because at least the way we did this experiment, or the way we hope the community sees this, is that clearly there's something missing in the theory. We have a very good theory that works at low energies, but there isn't really anything at high energies. And that was one of the challenges we had with this work, was that we'd done the experiment and the data was there, but then we had no idea how to analyze it because simply there wasn't a model. And I guess that it's exciting as an experimentalist when you're looking at things where often the theory is ahead of experiment. So often you have a prediction and then the experiment comes and either sees that or doesn't. But it's also very exciting as an experimentalist when you get right to the point where the theory ends, or where the theory doesn't become very clear, or at least you have many models trying to explain the same thing. So part of the hope, I would say, more in the long run, is really that this would help improve the theory and then create better materials. And of course, applications to quantum computing would be one of them, because of course quantum computing is very nice, but for it to become useful quantum computing, not just sort of like lab or textbook applications, there's still quite a few challenges, mostly engineering and also in fabrication that we need to overcome. So maybe this could help there. But like I said, this is more in the long run. If you ask me where I see this maybe going sooner, so that's one of the projects I'm working on now as part of sort of in my postdoc, but following up from my PhD work, is energy harvesting. So it turns out that a slightly different system, but with a similar technique and setup, can be used to produce a thermal harvester. So basically something that, to explain this quickly, if you use your phone or your computer for long periods of time, as you probably notice, it starts to warm up. That's wasted energy. When you charge your phone, you want the energy in the battery to go into powering the phone. You don't want to warm up the phone. It's not a radiator. So if you could somehow tap into that energy collected and use it for useful work, you would have a higher energy efficiency. Now, it turns out that a device like this, again, different device, but same technique and fundamentally sort of the same working principle, can be used to create a thermal engine, basically a system that will generate energy provided there's a gradient in temperature. And so if you couple that with whatever your device may be, and if that device, because it's not perfect, starts warming up, then it can tap into that waste of energy and start producing energy, which can then be fed back into the system of interest. And so that's what we call energy harvesting, and that's one of the things I'm trying to explore at the moment. Now, I sort of tapped into this at the end of when I was talking about the paper, because then you can say, okay, that's nice, but if this only works at low temperatures, it's not as if you can put that device inside my computer. And no, you can't, but maybe you can put it in anything in outer space, because this should work at 1 Kelvin, 4 Kelvin, and that's the typical temperatures you have in outer space. And so that's more direct application that I would like to explore, is more in terms of production of energy in space. By creating these sort of like very small devices that then can be integrated in a semiconductor chip. But yeah, there's, I guess there's a sort of like the long run direction where maybe this will go in, I don't know how many years, maybe I won't be alive, and more the in the short term, maybe 5-10 years from now, what I'm currently exploring as a proof of principle kind of for energy production. But I guess it's like everything in science. You think it will be used for one thing, and then it ends up being used for something completely different.
Yeah, I agree, and that's why it's so important to fund basic research without having to put like a direct purpose in there, because
Yep.
yeah, we don't
Exactly.
leads to, and that's so important. And
At the end of the day, what I'm doing is studying electrons in 1D. So yeah, it's almost playing with them and seeing what things happen, what you can see.
did Elon Musk, did you write him that you should use
What's there?
by Elon Musk, did you write him for his Mars mission? Like give you money? You can
Yeah, no, exactly. Give me money so I can keep doing this.
exactly. Then you can use it on Mars, maybe.
Yeah.
Jacob, Frank, Ben, did you have more questions, or people in the audience? Did you have more questions for Pedro? The hour is almost up, so there would be time for maybe 1 or 2 questions.
Well, first of all, Pedro, thank you so much for the presentation. I'm listening closely. I probably you've answered my question in the past 15 to 20 minutes. I have this question that let me put it just plainly again, because we didn't ask it in a plain way. What are you described yourself as an experimentalist, and now that you found such a thing, right? What are the preconditions, the necessary preconditions? What's the environment needed to find something surprising like that?
The environment in terms of experimental conditions.
Well, this is really a very broad question, just as general as you would make it. I have no
Okay,
specific
sure.
direction.
I guess, I mean, experimentally, if you go to any physics lab these days, at least when you're doing fundamental research or, I mean, I don't like using the word fundamental because, but what I mean by this is essentially doing research for the sake of research, not research with the intent of maybe having a commercial product 5 years down the line. That was never the goal with this project. But if you go to most physics lab, and not just physics, chemistry, any field really, normally the conditions in the lab are not are things where you need incredibly specialized equipment to achieve, and then you sort of see something, you understand, and then you try to make it work at more favorable conditions. Those conditions may be, in my case, low temperature, so like I said, minus 273 Celsius, maybe high pressure, so thousands of atmosphere, maybe very low vacuum, as in lower than the vacuum of outer space, maybe very small systems, so nanotechnology at the nanoscale or smaller, very powerful lasers, all of those conditions where you just don't have in your daily life. And really you're pushing, you're forcing these systems to happen, to these kind of effects to happen, and maybe I think it's one of the things you don't realize until you do the experiment itself. If I tell you I'm doing a measurement, for example, what I'm doing now at 300 millik, and then I do a measurement at 5 millik, maybe this doesn't sound like a big difference, but it's 2 orders of magnitude difference almost. And in nature, many things follow power laws. And so by changing those orders of magnitude, you can suddenly start seeing completely different things, completely different behavior. If I saw, you may look at the panels, for example, in figure 2C, and you see, oh, yeah, I have such nice parabolas and resonance. But if you were doing this above 10 Kelvin, which is still minus 260 degrees, so you would say, oh, that's still very, very cold, you wouldn't see any of this. You would just be completely blurred out. You would be completely washed away. So it's often the case that you change your experimental conditions slightly, and suddenly it's like almost a completely different system, or because different things come at play. So I think on the experimental side, those are the conditions. Of course, then again, in hindsight, I'm here telling you about, and the paper is written, and we have analyzed the data. But when you see this for the first time, you're very skeptical. I mean, for the first 2 years of my PhD, we were trying to fit this with a single parabola because we have this preconceived idea that that's what it should be. And I think that's often the case in science. You have this conceived prejudice. And then you go around until the scientific method forces you to accept other possibilities. So being in a lab and being surrounded by people with different expertise, and I like I said, I am an experimentalist, but I quite like to talk and collaborate with theorists, because if you try to do experiment without theory, it's like a shot in the dark. Like you might stumble across something, but the odds are much smaller. So yeah, I hope I answered your question, but
Absolutely,
yeah,
of course. We
yeah,
could go on and
yeah.
discuss all sorts of things. Yeah, but thank you very much.
Yeah, thank you for that interesting question. And yeah, I think like that you're in academia able to discuss openly your research is also
Yeah.
really important because I've been also working for industry, and there's kind of the opposite environment. And I feel like there's sometimes like stagnation because people are not allowed to talk about their research, so they go around in circles because they're kind of more on their own doing stuff. So
Yeah,
and
we do have that in our lab because, as you probably know, the semiconductor physics group also, there's a big industry in semiconductors. So some of my colleagues work for Toshiba or Hitachi, and of course they're not allowed to discuss their research or their results. They normally don't publish, they patent.
Mhm.
So um, I guess it's different way of communicating, but yeah, that kind of work is more industry focused rather than just academic research. Not that they don't do research, it's just normally contextualized for a given product or with very set deadlines, while here is more open-ended.
Yep. So thank you so much for sharing your work and some background stories around it, and answering all of our questions. That was really quite remarkable, your work, and the how you presented it. So we really appreciate it, and
Yeah,
feel
thank you for inviting me. It was really nice.
yeah, feel free to come back anytime if you one day maybe have something new to share. Yeah, or
Hopefully.
come by when we have discussions like this. It was yeah, it was, we really appreciate it a lot. Thank you.
Thank you. Yeah, I can just add one quick thing in case someone's interested. So there's actually a follow-up paper to this, which is currently under review. But if you go on archive and you look up my name, you'll quickly find that I don't remember the title now, but it's something like decoupling the spin and charge mass or something like that. It's the electron mass. So yeah, it's a follow-up paper to this work, and but yeah, thank you for inviting me. It was very nice, and if, if anyone has any further questions, feel free to contact me. You can find my email easily. And yeah, thank you.
Yeah, that's so nice of you. Thank you. We really appreciate that. And yeah, thank you everyone for coming, asking questions, um, commenting in the chat. Of course, thank you. And yeah, if you like discussions like this, follow the club. We have guest speakers here that come and share their research, that are generous like Pedro with their time. And yeah, I hope to hear you all back soon. And enjoy your weekend, Pedro, and everyone
Yeah,
else.
thank you.
And yeah, did you get to travel to Porto in the summer at
Not
all?
yet. I'm hoping to go maybe in September. Yeah, I haven't been home in a while, but yeah, I'm
Yeah,
hoping to go there soon.
yeah, yeah. Good luck. I hope monkeypox, other pandemic, doesn't get in the way again.
Yeah. I mean, yeah, same. I mean, I was yeah, the past 2 years I've traveled very little back home exactly because of the same.
Yeah, exactly. Me too. But anyways, okay. Good luck. We wish you all the funding, and
Thank you.
and enjoy your weekend, everyone. Thank you for coming. I'll
Thank
close
you.
the room.
Bye.
Bye. 3, 2, 1. Bye, everyone.